Hey guys, welcome back to the shop. We've got some electronic repairs to do today, specifically some circuit board repairs. I've got a couple of these I/O boards out of Yasnek MX3 controls. I think they're common to almost all the Yasnek controls. Anyway, I got two of these boards that are the same, and they both are broken. So, see if we can fix that. I think it's going to be pretty easy. And then I've got a Fagor digital readout, an old one, that we need to work on. That's probably going to be the first thing we'll do. I'll probably split this up into multiple videos just so it's less confusing. But anyway, I'm in my little electronics lab over here, and we're going to take a stab at fixing some of these things. But I thought before we get started on that, maybe we could talk about some ground rules or some background information that I've been able to put together about circuit board repairs and maybe about electronic repairs in general. But I don't claim to be an expert about fixing circuit boards or even electronics. This is a whole trade. Guys spend their whole career, trying to master fixing these things, and you need a lot of specialized tools. I kind of hack my way through it, but I don't have everything that I need to really do the job. So anyway, don't take what I say as gospel, but I have picked up a few, little pointers that might help you guys along the way. So I think what I want to say is that when it comes to fixing circuit boards specifically, in my opinion, it's not always necessary to know exactly how the thing works in order to fix it. So for example, we're talking about this circuit board probably in a second video, but this is an I/O board for a Yasnek machine, and it's all through hole components, pretty simple board, but this is a 3-level board with probably 300, 400 different components on it, and I have no schematics, I have no wiring diagrams, I have no information about how this thing actually works. What you're looking at is everything that I have to go off of. So I still think we can fix it, but I cannot tell you exactly how this thing works or exactly what all these chips do. Now maybe if you watch a channel like Mr. Carlson's Lab or Dave Jones at the EEV blog, he could point at these things and say, that's a shift register, or that's a hex buffer, or whatever, But a lot of times with these machine tool circuit boards, like you see these things here, these are hybrid chips, or basically it's basically like a little circuit board that's soldered onto the circuit board itself, and there's some numbers on there, but there's no manufacturer, there's no schematic, there's no nothing for that. So if you have a problem with one of these hybrid chips, you're kind of on your own. But I still think we can fix it, because the second thing that I've learned about circuit boards is that there's basically 2 ways that they can fail. So the least common way that a circuit board fails is some kind of catastrophic destruction. Like let's say the thing was powered up and somebody just opened a beer bottle and dumped it on top of it. And whatever, there was some high voltage going through this thing and it just fried every chip on the board. That's a catastrophic failure. When that happens, it's going to be very hard to recover. To give you a couple more examples, I had a customer that had a machine with a Dynapath Delta 20 control. I went in, looked at it, low voltage power supply was bad, told them they needed to replace it or repair it. They chose to buy a used one, put it in themselves, and somehow or another the guy hooked up the 110 volt input to the power supply on top of the 12 volt output. So he basically provided 110 volts AC power to every component in the machine that was looking for 12 volts DC. So, where do you even start trying to fix that, right? Every circuit board in the machine is basically fried at some point, because they're not designed to handle that kind of power. Another example I can think of, there was a shop here locally that had a Fagor that had the Hydro Sweep system. If you've never seen a Hydro Sweep system, it's basically it's this goofy system that Fagor came up with that kind of works like a chip conveyor. Has a big high volume coolant pump that flushes chips towards one end, and it has this big crazy wheel, like hamster wheel thing that fishes the chips out. Anyway, there's like a hose that runs along the back of the machine underneath the electrical cabinet, and somehow or another they blew up that hose and basically just filled the electrical cabinet full of coolant while the machine was powered up. And again, where do you even start? It destroyed every circuit board in the machine, so they ended up scrapping that thing. That's very rare though. What happens most often with circuit boards is that some component or even some small group of components fails, and then that section of the board just shuts off. Everything downstream of that circuit stops working. Almost always when solid-state electronic components fail, they fail open. And when the circuit's open, there's no more current flowing and no damage can be done. Now there are exceptions to that rule. Usually the big exception I see is with IGBT modules, like big switching transistors, especially like in spindle drives and VFDs. A lot of times when those fail, they'll fail closed. And I have seen machines burn or catch on fire because of that. The braking resistor switch will fail closed and basically just start pouring DC bus voltage into the braking resistor all the time. It's such a common problem that a lot of machine tools actually have a thermistor, like a thermometer basically, that measures the braking resistor temperature, and if the thing gets too hot, it'll e-stop the machine, basically throw the contactor for the drive. It can happen, but what I wanted to say, I guess, was, normally speaking, you just find the thing that failed, replace it, and away you go. So I guess that brings me to the third thing that I've learned, which is that you cannot fix a circuit board if you can't test it. And I don't mean like testing individual components. What I mean is testing the circuit board itself for function. So I've had people contact me, through YouTube or whatever, asking if I could repair different, circuit boards or components for their machine. And I almost always say no, because if you just send me a board and I don't have a machine that uses that circuit board, I have no way to test it. So even if I replaced every component on the board, I wouldn't know if it actually worked. So, in this case of this board, I have a machine that has a YASNAC control. I can plug the thing in and pretty quickly find out whether or not it works. Now in the case of this digital readout that we're going to look at, it's a self-contained unit. So everything that it needs to power up and function is built right into it. A lot of times, the expense in repairing an electronic component like this is in the test equipment. It's not in the actual work. So, okay guys, here's this Fagor digital readout unit that we're going to work on today. And just from looking at it, I would say it's pretty old. I don't know exactly how old it is, but sometime in the 80s I would guess, because they would have gone to a membrane keypad, by the 90s. So I would say sometime in the 80s this thing was built. But the problem is I've got it plugged in right now. Flip that on and you flip the switch on and nothing happens. There's basically nobody home. So we need to figure out why we're not getting any power. Okay, so all I've done at this point really is cracked the thing apart, and I have taken this board off its mounts and had a look around. I got a suspicion of what's going on, but all that's really happening in here, this is the back side of the front panel. This is the brains of the operation. It also handles all your inputs and outputs, and then this multi-pin connector here is what provides power to this panel right here. And I would suspect there's nothing wrong with this panel here. So I think we're probably going to find that the problem is somewhere in here, probably in this circuit board. So right away I can tell that we're dealing with a linear power supply, and the way I can tell that is just because of the size of this transformer. So a switch mode power supply, you take the power, your incoming power, AC power, rectify it to DC, send it through some kind of inverter, chop it up into a super high frequency, send that through a transformer, then take the opposite side of the transformer, rectify that back to DC, and then that's your basically DC power. And the reason they do that is so that they can use a very small transformer. But this thing has this great big transformer, and that leads me to believe it's a linear power supply. Also, just look at how simple this circuit board is. So with the linear power supply, we're just taking our AC voltage in, comes in down here. It's going into a transformer, and it's transforming it down to an AC voltage that's fairly close to the DC voltage that we want. And then it's going to go through some diodes, a bridge rectifier basically, and that's going to convert that AC into DC. We'll filter it through some capacitors, and then away we go. Now the drawback to the linear power supply is that they're very expensive because you have to have this great big transformer, and they're also sort of inefficient. But they do make some pretty nice clean power, so you'll see them a lot of times like in high-end audio amplifiers or old school digital readout units like this. I would imagine that any new digital readout unit would have a switch mode power supply instead of this linear power supply, but I don't know that for sure. So anyway, I've gone through and done the basic tests. There's a fuse here and a fuse here. Both of those fuses are good, so that's not the problem. I did check the switch. The switch is working, so we are getting power from our plug to the switch to the board, but then once it gets to the board, it stops. And all these wires and stuff right here, that has to do with a multi-tap for the transformer. So this power supply is able to operate on 240, 220, 120, or 110 volt. So basically by rotating an insert in this thing here, it just changes the taps in the transformer. But it is tapped correctly. I verified that, so that's not our problem. But I don't think we're going to have to go too far to find the problem. Some of you may have already spotted it. Let's see if we can take a closer look at these batteries here. So right here we've got a pair of NiCad rechargeable batteries, and those are there to basically keep the measurement. So when we power the thing off, next time we power it back on, it's going to go right back to 0 unless we use the batteries to maintain our encoder reading or our scale reading. So take a look at the crust that's growing on these batteries, and it's gotten down onto this resistor. It's creeped up the side of this little trim pot here. So we got some bad stuff going on here. Basically the electrolyte or acid or whatever is inside these batteries has long since spilled out and gotten onto the circuit board. So the other thing that jumps out at me right away, look at this big capacitor. See how it's all dented and screwed up? So I don't know what's going on with that. Then if we look at this post right here, it looks like this capacitor has been leaking a little bit too. So that's definitely a problem. So the back side of this board really tells the story. So first thing, this is a single-sided board, which is very nice. Should be really easy to work on. But the problem is, see all this corrosion here? That acid or electrolyte from that battery has just destroyed the back side of the board. It's peeled all the solder mask off, and basically any connection or solder joint that's in this area right here, which is 60% of the board, is now suspect. So this, you see where I bodged this wire in right here. Basically this is the output right here to the transformer, and I wasn't getting any voltage there. And basically this huge plane of the board right here, it's actually broken somewhere in here. The whole trace is missing, and I just bodged in this wire to see if I could connect the dots. And then if you look down here, there's a big section of this trace that's also missing, and I've had to fix this solder joint and this solder joint. They're both bad. And also I can tell that somebody's been in here before us. So you see these kind of crusty looking joints right here. Those are the electrolytic capacitors. So looks like somebody's probably replaced those caps one time before. And then if I'm not mistaken, it looks like they've replaced the diodes too, because this does not appear to be a factory solder job here. Or if it is, it's a pretty bad one. So this ain't her first rodeo, that's for sure. But I think first things first, we're gonna try to get rid of these big batteries, just get that crap out of there, and then we'll do our best to try to patch up the rest of this board. It is not going to be pretty when we get it done, but we should be able to get it to function. So I just touched up all these solder joints with some flux and some fresh solder. We'll see if it does any good. This board is nasty. You heat it up in the flux just bubbles out nasty stuff. It's just isopropyl alcohol. Yeah, bad shape. Yeah, see how nasty these pads are. But some of them have actually lifted too. Looks like that one lifted the pad quite a bit. So, I don't know. We'll do the best we can, I guess, and we'll just bodge wire the rest of it. Okay, I've cleaned up the board as well as I can. So now what I'm trying to do is just figure out what things are making a good connection and what is not. So I've got my multimeter set up here to measure continuity. And it's not the greatest test because this is going to be just a few milliamps of load. And some of these traces are going to be carrying, you know, a lot of power. But we'll give it a shot here. So everything on this big trace here should all be common. So we got good connection up here, but anywhere that's down here and corroded is, I got nothing here, 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 here. So basically it must be broken in here somewhere. Yeah, it's good there. But yeah, somewhere in here it's broken. Well, let's see if we can mark that. So we got a problem there. Now, if we look at the bottom side of it though, those are good. Okay, that one's not working. No. Okay, we got continuity there, but nothing there. Nothing there, nothing there. Okay, so we must be broken here and here. Right? Boy, it looks good there. I don't know why that doesn't make continuity. That one's good. Okay, now I gotta check this big guy here. I think this is the ground trace. Good. Okay, this one's no good. No good. So we know that one's broken right here. That one's good. That one's good. That one's no good. Okay, let's try this one here. Good. Good. No good. Okay, so we got a few things to fix. Okay, I think we've got it hacked back together. So I had to patch it here, 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 and then obviously this big bodge wire here. So I didn't show me doing that because it's really finicky work and it took me a lot longer than I expected. What I usually use for these short patches like this is these little tails that you get off of like resistors or capacitors when you install them. You install the through-hole component, you solder it, and then you cut these tails off. And they're already tinned and they're pure copper, so I find that they work really well for making these little patches on boards. I don't know if that's an approved method, but it works pretty good for me. So, and I wanted to use this piece of wire for this trace because that's a big trace and I don't know if it carries a lot of amps or what. But anyway, we're going to put it back together and see if it works. Okay, grab the fire extinguisher. Here we go. Well, it's doing something. What does 4 mean? Okay. Now we've got a 1. I wonder if it needs the encoders or the scales hooked up to it in order to function. Alright, there's 2 LEDs on this power supply board, so when I flip the switch I get both of them on. It's got to be a good sign, right? I think one tells me the capacitors are charged and the other one, I have no idea. Let's go plug it in. Okay, we've got it plugged in and the scales are hooked up, so let's give it a whirl here. Okay. 3. Okay, what did I do before? I think this button, I have no idea what it says. It's all worn out, but I think if I push this, boom! So you can switch between inches and millimeters, looks like. That's a good deal. Now, does it count? Oh yeah, look at that. Cool. I'm calling it fixed. Well, real quick, let's check the voltages that are coming out of that power supply, just in case somebody else has one of these and wants to know what the correct voltages are. So what I expect to see is probably like a 12 volt signal that runs all this nonsense, and then there's going to be a differential signal, like a plus 5 volts, minus 5 volts. That's pretty standard for an encoder, so we'll see what she's got in here. Okay, so we don't have a wiring diagram, but let's take a guess here and say black is the ground. It's a pretty good guess. It's like we got half a volt maybe, so that's probably the ground. There's a green wire, but that's definitely not ground. So we'll say black is ground, and there's our plus 5 volts. It's more like 5.5. There's our minus 5 volts. That one's pretty close. There's plus 5 volts again. Plus 5 volts. That looks like another ground. Plus 5 volts. And there's our 12 volt signal right there. Ah, come on. So there's our 12 volts. So, pretty good guess, huh? Okay, cool. Man, I can't believe how much heat this thing makes. All that's on that heatsink is those 3 little transistors, but that thing gets nice and toasty. Now, you definitely wouldn't want to run this for more than a few seconds without those transistors being bonded to that heatsink. And I did use some new heatsink compound when I put those on. So, cool deal. Okay, that's probably going to be it for this video. Now, I've still got some work to do. I need to probably replace this capacitor, and then figure out what to do about these batteries. Obviously, we're not going to put these back in. Anyway, I think there's plenty of room inside this housing. Probably what we'll do is we'll find a little battery pack that's easy to replace the batteries in, and we'll just run some wires over to the board and keep the acid away from the actual circuit board. Seems like a safer plan. Okay guys, thanks for watching, and next time we're going to fix this little circuit board and its newer cousin, and it looks like a pretty complicated deal, but we've got a little clue right there. So stay tuned for that.